The conventional flush toilet uses roughly 1.6 gallons of potable drinking water per flush in modern efficient models, or 3 to 5 gallons in older units, to transport human waste through pipes to septic systems or municipal sewage treatment plants where energy-intensive processes attempt to separate water from solids before returning treated water to the environment. Across typical American households, toilet flushing consumes 20,000 to 30,000 gallons of treated drinking water annually while generating similar volumes of wastewater requiring treatment at substantial public or private cost. The systemic irrationality of using treated drinking water as a waste transport fluid has been recognized for decades but remains firmly embedded in American residential construction due to regulatory requirements, cultural expectations, and industry inertia rather than technical necessity. Composting toilet technology provides an alternative approach that eliminates water consumption entirely, while producing agricultural-grade soil amendment from waste that conventional systems treat as disposal problem. The resulting systems can reduce household water consumption by 20 to 35%, eliminate septic system costs for off-grid applications, and produce valuable garden soil amendment for interested homeowners. Understanding how composting toilets work, what approaches suit different applications, and what practical considerations affect real-world performance reveals one of the most environmentally impactful residential technologies available despite its persistent marginal status in American markets. The fundamental biology of composting toilet operation depends on aerobic decomposition processes that transform human waste into stable humus-like material through microbial activity. Proper composting requires adequate oxygen supply, appropriate carbon-to-nitrogen ratios, sufficient moisture content, and adequate temperature maintenance. When these conditions are properly managed, composting reduces waste volume by 80 to 90%, while eliminating pathogens through combined heat and biological action. The resulting material resembles rich garden compost in appearance, odor, and biological characteristics, providing agricultural soil amendment rather than disposal problem. The biological process have been well understood for decades and operate reliably in properly designed systems. The traditional composting toilet adoption across Scandinavia, Australia, and New Zealand demonstrates proven technology applicability in developed world contexts with high sanitary expectations. Sweden, particularly, has supported composting toilet development and deployment, with hundreds of thousands of systems operating successfully in residential applications. Australian regulatory frameworks explicitly support composting toilet deployment in applicable contexts. The international experience validates composting toilet technology as mature option, suitable for mainstream applications rather than experimental or alternative lifestyle niche. The deployment history provides substantial real-world evidence supporting broader American adoption. Dr. Ingvar Blomqvist Jonsson, a Swedish-American environmental engineering researcher who has studied composting toilet performance across diverse residential applications, has documented how modern composting systems deliver sanitary outcomes equivalent or superior to conventional septic systems at dramatically reduced water consumption. His research at major American universities examines comparative performance of composting versus conventional systems across typical residential configurations. The research findings provide evidence-based foundation for understanding which approaches deliver greatest benefits in specific circumstances. The scientific foundation supports regulatory frameworks that might accommodate composting technology more widely than current American codes provide. The various composting toilet approaches span substantial range from simple to sophisticated. Self-contained units integrate waste collection, composting, and storage into single toilet-mounted assemblies suitable for applications with limited space. Central composting systems route waste from multiple toilets through chutes to basement-level composting chambers, supporting larger households with multiple bathrooms. Continuous composting systems maintain ongoing composting with periodic end-product removal. Batch composting systems fill chambers completely, seal them for composting, and replace them with fresh chambers during active use periods. Each approach suits specific applications through different design trade-offs between capacity, space requirements, maintenance patterns, and performance characteristics. Obinna Chukwu Okafor, a Nigerian-American sustainable sanitation consultant who has installed composting toilet systems across diverse residential projects, has documented how system selection substantially affects long-term owner satisfaction and operational success. His installation experience demonstrates that matching system capacity to household size and usage patterns prevents the overload problems that affect undersized systems. The professional sizing guidance often delivers value exceeding its modest costs, supporting informed system selection over generic product choices. The urine separation technology in modern composting toilets addresses historical odor and moisture management problems affecting earlier generations. Urine diverters collect liquid waste separately from solid waste, preventing the excess moisture accumulation that causes odor problems in improperly designed systems. The separated urine contains most of the nitrogen and phosphorus content of human waste, providing concentrated fertilizer value while simplifying solid waste composting. The urine separation represents important design evolution that substantially improved composting toilet performance and acceptance compared to earlier mixed waste approaches. The ventilation requirements for composting toilets substantially affect both performance and odor management. Properly vented systems maintain negative pressure in composting chambers, drawing air through the system and exhausting it through external vents that prevent any odor migration into living spaces. Passive ventilation using thermal buoyancy provides adequate airflow for many applications. Powered ventilation using small exhaust fans improves performance in marginal installations. The ventilation quality substantially affects user acceptance and long-term system success in residential applications. Now for the obstacles and limitations affecting composting toilet adoption. First, the regulatory barriers in most American jurisdictions substantially restrict composting toilet deployment. Most building codes require connection to sewer systems or approved septic systems, treating composting toilets as supplementary rather than primary sanitation. Some jurisdictions explicitly prohibit composting toilet primary use. The regulatory restrictions affect deployment even where technology performance would clearly support adoption. The regulatory modernization required for broader adoption faces political resistance despite technical justification. Second, the cultural resistance to any visible connection with human waste affects consumer acceptance substantially. American consumer expectations heavily favor flush toilet approaches that immediately remove waste from view and awareness. The periodic compost removal requirements of composting systems require direct user interaction with decomposed waste that flush systems eliminate entirely. The cultural considerations affect adoption beyond pure performance considerations, limiting market appeal to households willing to overcome conventional expectations. Third, the maintenance requirements exceed those of conventional toilets substantially. Regular chamber turning, moisture monitoring, and eventual compost removal require ongoing attention that flush toilets don't demand. The maintenance commitment affects household compatibility with composting systems, particularly for households with limited time or physical capability for the required attention. The maintenance considerations deter adoption among households prioritizing simplicity over sustainability performance. Fourth, the installation complications in existing homes affect retrofit applications substantially. Adding composting toilets to homes with existing conventional plumbing requires substantial plumbing modifications or installation of composting toilets as supplementary rather than replacement systems. Some composting system approaches require substantial floor space below toilets for composting chambers that existing home floor plans cannot accommodate. The installation constraints particularly affect dense urban housing, where space limitations compound regulatory restrictions. Fifth, the compost handling and end product use requires appropriate outdoor space and homeowner commitment. Apartment dwellers and small lot suburban homeowners often lack suitable space for compost finishing and end product application. The urban applicability limitations affect market potential in dense residential contexts where water conservation benefits would otherwise be particularly valuable. The space requirements reinforce composting toilet applicability to rural and suburban contexts with substantial outdoor space. Despite these considerations, composting toilets deliver substantial environmental benefits and cost savings for appropriate applications and deserve serious consideration for off-grid projects, rural homes, and environmentally motivated households in supportive jurisdictions. The economic analysis of composting toilet investment varies substantially across applications. Off-grid applications eliminating septic system costs entirely achieve dramatic net savings despite substantial composting system costs. Rural applications with conventional septic replacement considerations sometimes favor composting approaches. Urban applications with existing sewer connections rarely achieve favorable economics due to minimal savings from reduced water consumption alone. The application-specific economics require case-by-case analysis rather than generic recommendations applying uniformly across contexts. Mariama Diallo Sow, a Senegalese-American rural sanitation consultant, has documented how composting toilet adoption in appropriate rural applications delivers substantial lifetime cost savings compared to conventional septic alternatives. Her analysis shows that off-grid cabin applications save $10,000 to $30,000 in avoided septic system costs compared to composting toilet installation costs of $2,000 to $8,000. The off-grid application economics strongly favor composting toilets even before considering ongoing operational savings from water consumption elimination. The water conservation benefits extend beyond individual homeowner economics to include substantial regional resource management benefits. Widespread composting toilet adoption could reduce residential water consumption by 20 to 30% nationally, providing substantial benefits in water-stressed regions. Municipal water system capacity improvements from demand reduction defer infrastructure investments. Wastewater treatment system capacity improvements similarly defer treatment plant expansions. The aggregate benefits support public policy attention beyond individual homeowner considerations. Dr. Hongming Chen Wang, a Chinese-American water resource engineering researcher, has documented how residential water conservation through composting toilets and similar technologies could dramatically reduce regional water stress in American Southwest applications. Her research shows that 10 to 15% residential water consumption reductions could eliminate projected water supply gaps in several stressed regions across coming decades. The water resource framing supports composting toilet advocacy beyond individual homeowner benefit considerations, connecting technology adoption with broader sustainability goals. The soil amendment benefits of finished compost provide additional value for homeowners with gardens or landscaping. Finished humus from composting toilets resembles rich garden compost suitable for ornamental plantings, perennials, and most vegetable applications. Proper handling protocols ensure pathogen elimination before agricultural use. Some jurisdictions restrict food crop applications even for properly composted material, limiting agricultural application range. The soil amendment value adds meaningful benefit for gardeners willing to integrate composted humus with overall landscape management. Rashid Aliyu Musa, a Nigerian-American sustainable agriculture researcher, has documented how properly composted human waste provides soil amendment value equivalent to high-quality commercial compost at substantially reduced environmental footprint. His research validates finished compost from well-designed composting toilet systems as agricultural resource rather than disposal problem. The agricultural research supports composting toilet advocacy as complete resource management approach rather than merely water conservation technology. The off-grid cabin and recreational applications represent natural primary markets for composting toilet technology. Remote cabins, tiny houses, and recreational vehicles often lack practical access to municipal sewer or conventional septic systems. Composting toilets provide self-contained sanitation that eliminates dependency on impractical alternatives. The off-grid market represents substantial demand that drives continued product development and market availability. Many composting toilet manufacturers specifically target off-grid markets with products suited to these applications. The tiny house movement has particularly embraced composting toilet technology as practical solution for very small dwellings. Space constraints in tiny houses often prohibit conventional flush toilets and associated septic systems. Composting toilets integrate effectively into tiny house designs while supporting the sustainability values commonly associated with the tiny house movement. The tiny house adoption has substantially expanded composting toilet market visibility beyond traditional off-grid contexts. The visible, successful adoption in tiny house contexts supports broader market awareness. Luana Coelho Rodrigues, a Brazilian-American tiny house design consultant, has documented how composting toilets have become standard feature in quality tiny house designs, reflecting both practical space considerations and sustainability values common among tiny house residents. Her design experience demonstrates that properly integrated composting toilets enhance rather than compromise tiny house livability. The design success contradicts stereotypes about composting toilet compromises that deter conventional home applications. The urban application innovations emerging in Scandinavia and progressive American contexts demonstrate potential for broader deployment beyond rural contexts. Urban composting toilet installations serving apartment buildings, office buildings, and public facilities demonstrate technology scalability. Centralized urban composting systems that process waste from multiple buildings address space limitations affecting individual urban installations. The urban innovation suggests future market expansion beyond current rural and off-grid emphasis. The research on long-term composting toilet durability and performance shows generally favorable results with quality equipment. Mechanical components including ventilation fans, urine diverters, and chamber rotation mechanisms typically last 10 to 20 years. Composting chamber structural components often last 30 to 50 years with minimal maintenance. The modest long-term maintenance costs combine with substantial operational benefits to deliver favorable lifetime economics for appropriate applications. The durability supports composting toilet adoption as long-term infrastructure rather than experimental installations. The professional installation considerations for composting toilets exceed those of conventional plumbing in important respects. Proper system design requires understanding of composting biology, ventilation requirements, and local regulatory conditions beyond basic plumbing knowledge. Experienced composting toilet installers produce substantially better outcomes than general plumbers attempting first-time installations. The contractor selection substantially affects both installation quality and long-term performance reliability, supporting careful professional vetting during project planning. The graywater integration with composting toilet systems creates comprehensive water-saving sanitation approaches. Graywater from sinks, showers, and laundry can be routed to landscape irrigation rather than sewer systems, further reducing total water consumption. The combined blackwater composting and graywater irrigation approach delivers near-total elimination of household wastewater generation. The comprehensive water management represents emerging direction for sustainable home design that addresses sanitation, water consumption, and landscape irrigation through integrated approaches rather than isolated components. Adekunle Ogundipe Balogun, a Nigerian-American sustainable home design consultant, has documented comprehensive water management approaches combining composting toilets with graywater irrigation across diverse residential applications. His project experience demonstrates that integrated approaches can reduce total household water consumption by 60 to 80%, compared to conventional arrangements while supporting substantial landscape improvements through graywater application. The comprehensive approach represents best practice for sustainability-focused residential design in appropriate regulatory contexts. The carbon bulking material requirements for proper composting substantially affect system operation. Sawdust, coconut coir, peat moss, or similar dry carbon-rich materials must be added regularly to balance the nitrogen content of human waste and provide structural support for composting biology. The bulking material requirements add minor ongoing costs and sourcing considerations for system operators. Properly managed bulking material addition produces substantially better composting outcomes than simple waste collection without carbon balance. The temperature management considerations affect both composting performance and pathogen elimination effectiveness. Higher composting temperatures of 130 to 160 degrees accelerate decomposition while ensuring pathogen elimination through thermal inactivation. Systems in cold climates may require supplementary heating to maintain optimal composting temperatures during winter months. Systems in hot climates often achieve optimal temperatures through ambient conditions alone. The climate adaptation of system design and operation optimizes performance for specific regional conditions. The post-composting curing period ensures complete pathogen elimination and material stabilization before end product use. Compost from active chambers should be transferred to secondary curing containers for additional 6 to 12 months of further decomposition before any agricultural application. The curing approach ensures sanitary end product regardless of any variations in active composting performance. The conservative handling protocols maintain safety margins that support public health protection alongside resource recovery benefits. Consider what composting toilet technology means for off-grid applications, rural homes, and environmentally motivated households in appropriate regulatory contexts. The water conservation of 20,000 to 30,000 gallons annually eliminates substantial resource waste. The elimination of septic system costs delivers major financial benefits for off-grid applications. The soil amendment production adds agricultural value for homeowners with gardens. The proven international track record validates technology, maturity, and reliability. The modern urine separation and ventilation technologies address historical performance limitations. The tiny house and off-grid market applications demonstrate viable integration with contemporary lifestyles. The environmental benefits support water resource management in stressed regions. The research-based performance documentation validates technology effectiveness. The regulatory evolution in some jurisdictions supports expanded deployment possibilities. The soil amendment value represents secondary benefit beyond primary sanitation function. The long-term durability supports infrastructure-grade investment decisions. The international experience provides proven design and operational guidance. The question isn't whether composting toilets deserve consideration for appropriate applications. The question is Why technology with such substantial environmental benefits and proven international success remains so marginalized in American residential markets despite decades of demonstrated performance. The answers involve regulatory resistance, cultural expectations, and industry structures favoring conventional alternatives over sustainable alternatives. For off-grid applications, rural homes seeking septic alternatives, and environmentally motivated households in supportive regulatory contexts, composting toilets represent one of the most environmentally impactful residential technologies available in contemporary markets, despite their persistent marginal status. The aesthetic design improvements in modern composting toilet products address consumer acceptance concerns that deterred earlier adoption. Contemporary composting toilets feature ceramic or porcelain surfaces, modern styling, and overall appearance similar to conventional flush toilets. The visual differences between modern composting and flush toilets are minimal in installation-ready products. The design modernization eliminates aesthetic objections that affected earlier product generations, expanding market appeal beyond sustainability-focused consumers to households with mainstream design preferences. Dr. Kjell Svensson Andersen, a Norwegian-American product design researcher, has documented how aesthetic improvements in modern composting toilets substantially increased consumer acceptance across Scandinavian markets. The insurance and property value considerations for homes with composting toilets have evolved as the technology has matured. Older concerns about property value penalties have largely dissipated in markets where composting toilets are well established. Homeowners' insurance coverage generally accommodates composting toilets without premium increases. Mortgage qualification issues that affected some early adopters have largely resolved through regulatory normalization. The financial infrastructure maturation supports continued market expansion beyond early adopter contexts. The zero-discharge property applications particularly benefit from composting toilet integration. Rural properties seeking to eliminate all wastewater discharge for environmental or regulatory reasons can combine composting toilets with gray water systems to achieve genuinely zero-discharge status. The zero-discharge approach particularly suits environmentally sensitive locations near water bodies or conservation areas where any wastewater discharge would be problematic. The specialized application represents small but important niche where composting toilet technology provides solutions conventional alternatives cannot match. The educational infrastructure around composting toilet technology has expanded through homeowner workshops, manufacturer training, and online resources that support informed decision-making. Organizations including the Watershed Management Group, Oregon Tilth, and various cooperative extension programs offer educational resources on proper composting toilet selection and operation. Manufacturer documentation has substantially improved from earlier generations, providing clearer installation and operation guidance. The educational resource expansion supports broader homeowner engagement with the technology beyond specialized adopter communities. The pilot programs in several American jurisdictions have demonstrated composting toilet viability for expanded regulatory acceptance. Massachusetts, Oregon, and Vermont have documented successful residential composting toilet deployments that support regulatory evolution toward broader acceptance. The demonstrated successful performance in American regulatory contexts supports continued policy evolution that could expand deployment possibilities beyond current restrictive frameworks. The long-term cultural shift possibilities around composting toilet acceptance depends substantially on climate policy evolution and water scarcity responses in coming decades. As water stress increases across southwestern regions and climate impacts affect water availability broadly, sustainable sanitation alternatives, including composting toilets, may gain mainstream attention that current conditions don't support. The anticipated climate and resource pressure creates conditions that may dramatically accelerate composting toilet adoption beyond current niche applications. The technology remains ready for expanded deployment when regulatory and cultural conditions evolve to support it. The research community continues refining composting toilet designs and operational protocols through ongoing university-industry collaborations. Optimization of ventilation patterns, carbon-nitrogen ratios, and end product handling continues producing incremental improvements. The research investment demonstrates ongoing institutional support for composting technology evolution, supporting continued product improvements across coming decades.